For those who followed the SYCL for CPU last week, so we are doing the same now for GPU. I put on the SYCL course channel on the j'ai une absence. On Discord, yeah, on Discord, on the channel SYCL course. I put the names of the Git repositories to be cloned. In the GPU1, so you need, as usual, you need the setup and the GPU1, especially because the GPU1 for the practice is using the CMake files, which are given in the setup. If you want to have the slides live, you have them in the SYCL for in the GPU repository, in the slides subdirectory. And so let's go with a few reminders for those who followed the Thursday webinar, but perhaps new for the others. So a few information about how to use SYCL for GPU, and only focusing on the information that will be needed for the practice. So first point, when doing a SYCL program, you should create a queue, one queue by device. So in this practice, we are doing simply one queue. So now for GPU. So last week, we were seeing just a queue with the CPU selector, but as you see now, actually, you can select any kind of device. So if you say nothing when you're creating your queue, you will have the default, the same as if you say default selector. So there's a kind of runtime selection of what is the best device. So we could discuss a lot what is the best. So quite often it depends on the implementation you're using. Quite strangely, when you implement with an Intel implementation of SYCL, the Intel GPU has a good rank. But generally, if you have a discrete GPU on your machine, it will be the default choice. So if you say nothing, and if there's a GPU in your machine, it will try to run on GPU. So you must be aware of this. If you want to enforce a CPU, you say CPU selector. If you want to enforce a GPU, you may say a GPU selector. But actually, you may do something very complex because SYCL gives you much information on the available device at runtime. And you can write your own selector, so to make a complex mix, looking at all the information and the characteristics you can get about the device to choose the one you prefer. There, I'm doing. So as usual, you make it with a lambda on the fly. So there, I'm creating a queue with a lambda, which will select a given device. There, I have an example where I'm looking at a Boolean, and if this Boolean is true for Arc CPU, I will return the same as the CPU selector. And if I have this Boolean, this test on Arc GPU true, I will return the same thing on the GPU selector. But you can also make a complete fix thing using the information. For example, in this display, I'm showing that I can display the device name, the device vendor. But if you look at the reference about SYCL, you'll see that there are many information, the number of streams, whatever you can imagine. And you can, there's way also to say, okay, I want something when there is NVIDIA in the name, whatever you want. So first point, make the queue. I focus a little on this because it's in the genetic of SYCL to be able to be run anywhere, discover what is the device, what are the devices available, and try to choose the best one at the runtime. So the typical way, as we said last week, the original way to do computations with SYCL is to use buffers and accessors. So first you create buffers on top of your input data, your arrays, your whatever. Then you submit a job on the queue, which will be forwarded to the device. And then in this first step, you are creating accessors connected to the buffers. So the new things with accessors as compared to the buffer is that that's the place where you say, for this task, I will be read-only or write-only or both on all these sort of buffers. So that's the place where you give information to the system about who will read, who will write, where. So this first submission is made with a lambda, as usual, but this lambda is capturing by reference because until this point, we are still running on the host. We are not yet on the device. What we call usually the kernel in the GPU world, it's this CGH parallel 4. So that's where I'm submitting a new lambda, which is a kernel. This one eventually captures some values by some data by value because they will be duplicated on the device. And that's the kernel. There, I'm just doing a square of my input. And so you see, I access the data through the accessors, but I use them as the usual arrays finally. So the kernel is just this lambda, this internal lambda, capturing by value. If I want to look at the result outside of this computing, I will use this host accessor there, which is specific. It's when I want to access the data on the host side. And there I'm doing so this accessor on the output buff and just displaying the value there. The key thing also with buffers on accessors is that because you say who is writing, who is reading, the runtime organized for you what is done in which order. You don't need to mind about doing some weights there and there to be sure that the work is finished. In this specific example, when arriving on the host accessor will wait until what is done before on the queue is finished. And also, once you have done the buffer, remember that you should not access directly your initial input or output until the buffers have been destructed and give you back the end on your original arrays. So that's with buffer accessors. We have seen last week with CPU that actually we may use row pointers, so why not? I'm not doing any buffer, accessor, etc., just using directly my pointers there in my kernel. Because I don't use, you will notice also there's a shortcut. There I'm first doing submit, then accessors, then parallel 4 on the handler, which I received there. I have 2 levels of lambda. If I do not need to make some accessors, there is a shortcut. I can directly call the parallel 4 on the queue. That's what I'm doing there. I'm doing directly in one step queue parallel 4 because I don't need the intermediary level where I was making the accessor before. Because there's no buffers, I should do a wait before I'm doing the print on my output. But this actually on the GPU will not work. It was okay for CPU, but on GPU it will not work because my row pointers, they make sense when you are in the host code, but once on the device, they are not valid anymore. So there's a way to make these simple kind of things if you don't want to make buffers, accessors, etc. There's a way which is to use malloc shared. So there I was just doing a new, usual new in C++. Instead, I will do a malloc shared of float with a size. This malloc shared is attached to a given queue. You will notice this queue argument there at the end. And this will return something which looks like a pointer, a float star there, but which is usable both in the host code and in the GPU code. And what happens behind the scene is that I do not need to make any copy. Actually, it's somewhere at the system level that when the GPU needs something and use a pointer, it will trigger some kind of triggering some kind of copy because the system will notice, we lack the data, I will copy it. And if I use that same pointers in some host code and use it, he will see that, oh, I need some data which were modified on the device, I take it back on the host, etc. And so all of this, that's what they call in SYCL the unified shared memory. All of this is happening at some system level, and you don't care. It's automatic. So it's easy, very easy to create and use, and automatic. But as you will see in the practice, because it's so automatic, it's perhaps not the most efficient way. So that's what I call the easy, lazy way. Easy to write, not so efficient as it could be. It's potentially slower than using the buffers and accessors because this system lacks the information who read, who write, when, so improvise on the fly. So that's the shared memory, but you can push a little more in the control we take on anything, which is to use instead the malloc device. If you instead of the malloc shared, you are doing a malloc device, you are creating a pointer and a memory area which is only usable on the device, not on the host. And then you need more work. You need to explicitly copy data in it yourself. Instead of relying on the unified shared memory, which is automatic, you know what you do, and it's your job to do the copy. And that's normally the way you can be the more efficient because you know your problem, which steps are done at which moment, and so you do the copy, you do the malloc, and also you do the wait at the right moment. So for example, there, I'm doing my two input-output arrays on the device. There, I'm calling on the queue. Instead of submit, I'm doing a mem copy saying, take this, it's the size, the reverse size, I think. Take this input on my host, put it on the device input, the one I just created with the malloc device before. I give a size. There's another way to write it. I think in the practice we use the other one. This one is mimicking the C function. You give first the target, then the source, then the total size in bytes. You see I multiplied the size of my array by the size of a float. I realize now that there's a simpler one, which I use in the practice, where you say from, to, and the number of elements. And it is computing in the C++ way the size. Okay, so you're doing explicitly the copy. Then I'm submitting my kernel. Then I wait. And then I'm doing the copy back of the output on my host machine. So this one, in theory, is the most efficient, but you do all the work. You do the creation of areas, either host or device, you do the copy, you do the wait, and you hopefully should not make any error or you will not get the expected result. Sometimes when you are doing things one after the others, rather than saying wait after each thing you are doing to the queue, you see there, I have a wait there, I have a wait there, I have a wait at the end. Instead, you can do a queue where you say it's in a queue in order, meaning that whatever you submit to the queue will be done in the same order with an implicit wait before each step. It's not the default. The default is that if I ask many things to my queue, it may be run in parallel. So if you want this, if you are doing something quite simple, you rather use a queue in order and then it's okay. It's okay, but the only things which are in order are the things which are sent to the queue. So if at a moment you want to do something on the host, and the host need that whatever has been done on the queue should be finished, even if the queue is in order, it's not sufficient. You will need to add a wait before doing what was doing the host accessor before. Because the queue is in order, but if you do something in the host, you don't know what is the status of your queue. So don't think I put a queue in order and everything is automatic and okay because it will be done in the order I write it. It's only true for what is submitted to the queue, not what is happening on the host. There's a trap there. If you want to do something a lot more complex, we'll try to do one at the end of the practice. Actually, you should notice that when you are doing a queue memcopy, a queue submit of whatever, when you put something to be done, a task on the queue, in exchange, it is returning you an event, a cycle event. In all the example before, I was just ignoring this or calling directly queue wait after it. But actually, the function returns something, which is an event. And the event is the object that is able to say to you, I am finished or not. And it's also the object on which you call wait when you want to wait on the event. And sometimes you need to do some complex task graph. And not only you can use the event to say wait, but you can use the event in another submission to the queue saying you must wait for these events to be finished. There are prerequisites to be done before you start. So there, and again, you do this at the same place where we were doing the accessors between the submit and the actual action, kernel action. So for example, there, you see I'm doing memcopy, which return me this E1 event. And then when I submit my computation, I can say, so there I capture anything by reference, and I can say after my submit and before my parallel for, I must say my CGH, which mean actually command group handler. I can say there, it depends, the current action, it depends on U1, meaning that this computation will not be done before U1 is finished. And then I'm doing another computation, the copy back, and just the same, the submission of my square computation return me E2, and I put it in a depend zone on the copy back of the data. But as I said, I still need this final queue wait before I can look on the host, I can look on the results. There, if I want, I should have put event E3 equal queue submit and then say E3 point wait. Should have be more consistent with the rest of the example, but that's the idea. Just remember, anytime you submit something on the queue, you get back an event that can be used as a prerequisite for other actions. That's also, I think, if you want to do something with several queues, using several devices, you should be able to use this to synchronize between the different queues, what you cannot do with any other way. So that's for the events. So the practice. Oh, moving on. So as usual, better if you are at ease with the concept of the C++ Lambda, we put them everywhere. So you should have a clone of this Grace Code SYCL setup repository. If you are using Docker today, we will use those images, ICPX CUDA for the Intel implementation, ACPP CUDA for the adaptive CPP1. So you'll need to Docker pool them. You'll find in the slide, which are in the repository, the usual links to the reference guide, etc. This is the machine like last week where I'm doing my timing to check what is going fast or not. So today we will use this RTX A-simil for the test. For the numbers I'm giving, you will use your own on your own machine or servers. And so to get the training material, you should clone this Grace Code SYCL setup. Nearby this one, Grace Code SYCL GPU, and that's okay. Put the addresses also on the Discord. And so let's start. Okay, try to make it big enough. So that's the README of the Grace Code SYCL GPU repository. So just giving the usual information. You should have also the setup if you use the CMake from it. We will use, as compared to the complete Grayscott bench application, we'll use a simplified use case, just doing 50 images with 10 steps between 2 images to go faster for the demonstration. So new this year, you can use either Intel implementation or adaptive CPP1. Normally, I made some improvement as compared to last week. If you just run those kind of Coliru bash, it may be able to detect, oh, it's ACPP or oh, it's ACPX. If it does not, you can explicitly say Coliru ICPX CUDA or Coliru ACPP. First difference between the two implementations. When using Intel, as far as I know, but you can complete me on Discord if I'm wrong. As far as I know, when compiling with Intel, you must say in the targets, the SYCL targets, I want to prepare a binary for CUDA, or I want to prepare a binary for CPU, etc., for the kernels, I mean. With adaptive CPP, at least the recent releases, you don't need to. He will discover on the fly. He has some default setups and will discover on the fly that, oh, I need something for CUDA, I make it. So that's why I don't need to say, to have a specific CMake for CUDA with adaptive CPP, at least as it is installed on my machine. He will just discover on the fly. So for the automatic way to run on different machines, I found that ACPP was a little better on this point. So in the repository, you have different directories, device, demonstrating selection device, etc. We will see more after. And the practice are the directories named step 0 to step 5. Not sure if the 5 is the right number today. No, it's not up to date. The step 2 has disappeared, so forget about this. So let's start with the warm-up. So warm-up will start from a CPU code and move it to GPU, I think. So you can directly work in your copy or make your own MyGPU project. Have a look at the script which is doing the CMake execution, make execution, runtime with the arguments, etc. to see how it works. Or you can directly run it and see the demonstration. So the first step is just try to set up your environment, run it, and check what are the runtimes you got. I think I'm not sure what is the initial code. Let's check together. Where is my working work there? I will make it bigger. So let's inspect a little the starting code. So I'm in the Git repository named Grayscott SYCL GPU. There I will move to, we move to the step 0 directory, then give a look at SRC, and the starting code is Grayscott CPP. Also, I made a small difference as compared as last week. The code which is never changing, I move it to this Grayscott header file, just to review it quickly. So what I have in my standard header file, I'm saying that real for the practice is float. If you like, you may try to change using real for double just to see how it works and what's the performance. With these two constants, real 0 and 1, which I'm using there and there, the usual numbers for our Grayscott simulation, the usual pattern. You may want to use a different pattern if you like. There are better ones. That's the one we agreed on in the school. I have this code which is detecting and displaying, am I running on the output, am I running with adaptive CPP off with Intel? This drop function is the one which is taking the array representing either U or V in my reaction and putting a kind of drop of U in the V or V in the U in the middle. This function insert is taking my original image with the right size and duplicating it in an image which is just a little bigger with a border of 0 outside. Okay. Extract is doing the reverse, taking my image with the additional border, which has been computed, simulated, and taking the central part to put it back in my original output. Analyze, which is doing a kind of fake, very fake analysis, just doing some kind of mean value of my image, just to check I've not broken anything. So that's the other file, which will be the same all along the practice, so you don't care so much. Let's now review the original code, which I see is written with buffers. So where's the main? Here's the main. So I'm printing the compiler I'm using just to check I'm not mixing Intel and adaptive CPP. I'm taking on the command line number of columns I want, number of rows, number of image, iteration, etc. I'm checking it's multiple of those values because I will use them perhaps or not to try the ND range. I check the number of iteration is a pair because it will ease my code to be sure that when I'm doing my double buffering between the U1 images, the U2, that I will iterate an even number of things so that the final value is in the U1. Just to be sure, I'm using an even number so that I don't have to check every time if is the final value in U1 or U2, which is not the aim of this practice. There I'm recalling the arguments and then doing the actual job. So for the moment, I'm doing my queue with a CPU selector, so my starting code will work on CPU. I'm checking, getting the device information and displaying on the output, again to check where am I running. So there, I'm preparing two initial arrays of U and V. So with the size which has been asked by the user, I fill them, the U with 1 everywhere, the V with 0 everywhere. In my U, which has 1 everywhere, I'm dropping some 0 in the center with this dropped. In the V, on the contrary, I'm doing some V in the center with the 1s instead of the 0, okay? So my initial U is just 1 everywhere except at the middle where I have no U, and V is the contrary. And then I'm starting the process, and when finished, deleting U and V. So what is doing process images? Is initiating my result, which is a mean on all the images, just to be sure I have always the same result, okay? Then I'm doing my extended images. I'm adding a border of 0 for my stencil to work. So the size are the original ones plus 2. I'm doing those 4 arrays, U1, V1, U2, V2, so that I will, at each step, either take U1 as the input, compute the result in U2. Next step, taking U2 as the input, putting the result in U1, and again. So there I'm putting 0 everywhere. And as a first step there, I'm inserting, so I take the content of UH, meaning U on the host, in U1, which will be used in the device at the moment. I am there duplicating my original V host on V1 to start the process. So I have my collection of arrays on the host, UH, VH, U1, V1, U2, V2. For those ones which will be sent to the device, I'm doing buffers on top of U1, V1, U2, V2. And then starting to produce my images. So I'm doing NB images. Each time I will call iterate, which will do NB iterations. After each set of iteration, I will use these host accessors to take the values of VB1. So I'm doing V host accessors on VB1. I extract the corresponding pointer to call extract and to copy it in VH. So taking the buffer, where is the result? Which is in an extended image, extracting the result to put it in VH, which has the original size, then computing my pseudo analysis, a small dot, etc. So what is doing iterate? So iterate receive the queue, the 4 buffers. Each time I will take the first one and copy in the second one and swap. So I prefer to call, instead of U1, U2, I prefer to call them input U buffers, input V buffers, etc. I have the size, which is the extended size. So I will do NB iteration, and each time I'm submitting a job to the queue. So I submit, I do the accessors on the buffers, and then for the moment, not doing, just mimicking what happens on a sequential code on CPU. I'm not doing a parallel for, I'm just doing a call to a single task. If you remember last week, we have seen that if there I'm putting a parallel for, SYCL will try to do multi-threading. And we have seen that multi-threading on this process, on this use case, etc., is not efficient, does not pay for. We'll go faster, but using many cores and wasting many resources. So I'm starting from the point which were the better one with CPU, just doing a single task. And so the single task will, there I have the stencil. I'm doing 2 loops on row and columns. For each of them, I'm applying my pattern, computing the Gray-Scott formula, storing the result in my output accessors, and that's all. And once my submitting of a single task is finished, I'm swapping the buffers, which will just, it will not copy data, actually. It will just swap, as for a vector, it will swap the internals so that my U1 becomes U2, etc., and again, and again, and again, and again. So remember there we are using a single task because we don't want, we are on CPU for the moment, and we don't want to waste time with multi-threading, which is not interesting in this use case of now. So back, after the comment of the starting code, back to the practice. So try to run this, look at the numbers. You've seen I've run it on Cassidy. I'm not sure why, but I noticed that in my last test, Intel was running a lot slower than adaptive CPP. So the usual guess is one of them is vectorizing and the other not. But I'm not sure I can explain why, but that's not the focus of the practice, so not a problem. Perhaps you will see different things on your machine. And so the practice is to run, the first step is run on CPU, on GPU. So what you have to do, you replace the CPU selector with a GPU selector. Then you should notice, oh my God, it is very slow because we use a single task. So if my single task is running on a single thread item of the GPU, you can guess why it is so slow. So after the next steps is to replace the single task with a parallel for. And the third question, I will not give you the answer now, is why it is crashing at the end of the job, of the work. So try to figure out why it is crashing and solve the issue. And if you are in a hurry, you may look not too fast, I hope, but you have the Grace Code Soul as a solution. So let's try this for 5 or 10 minutes. I will, in the Discord channel, I will put my usual poll. Have you succeeded or not? To be sure, at least one of you has finished the exercise before we go on. So please, if you do this, understand, find the crash, solve the issue, go to the poll to say I'm okay, so that we can see that some of you are progressing. So I'll let you try. We'll start the poll. So replace the CPU selector with the GPU1. Straightforward. So that's slow because single task running on just one computing item of your GPU, of course, not optimal. So you put the parallel for using the full GPU and it should be okay. Let's see the crash, the reason for the crash. Quite easy too. What's the problem? Let me check in process image. You see there, I'm creating my U1, V1, U2, V2 with my command new, prepare them, do the buffers, and finally deleting my U2, V1, etc. as expected. I've done the new, I'm doing the delete. The problem is that I delete them first, and the buffers, they will be deleted after when I'm at the closing curly brace. They have been created there with usual object on the stack, and they are destructed when I'm closing the curly brace of the function. So I destroy the buffers after I destroy the arrays which are underlying, which are under the buffers. That's why I have a crash. Normally, until the buffers is destroyed, you should not touch the underlying arrays. So if you destroy them, of course, when you arrive to the destructor of the buffers, it will crash. So you must change something. So I'm not sure what I did, but in the solution there, yeah, I moved the creation and destruction of U1, V1, U2, V2 from process image to the main function. And I just left the process image to make the buffers. So to be sure that the buffers are destroyed first. But just remember, you use buffers, you should not touch the arrays, not read them, write them, nor delete them before the buffers have disappeared. For what concerns the timing and the performance, so also one point which may be important, especially with SYCL. Remember, SYCL has in mind, I run anywhere, I discover on the fly what's on the device, and sometimes I discover a new hardware and I recompute my kernel on the fly to adapt to the GPU I'm founding where I'm running, okay? So there's on-the-fly compilation, final compilation. Sometimes I think that with Intel, etc., for GPU, NVIDIA, the kernel is first compiled in some SPIR-V intermediary representation. And when arriving on the final real GPU, transform this in the final binary on the fly. So the first time you run a program in a given place, you will have those additional time taken to finish the compilation, to complete it. So if you want to do some timing to have a guess of what is going on, you must run your program at least twice, because the first run will finalize the compilation, okay? That's why if you want to have a look and see if it's performing well, you run it at least twice. In my test, I run them 6 times generally. I throw away the first one, which is finalizing the compilation and doing some kind of taking the median value for the 5 other ones. And so in Cassidy, I got this. So you see, also, as I said there, that's a practice. That's not a benchmark. Don't take the numbers and think, oh, okay, Intel is going faster, adaptive CPP is going faster. The numbers, if you run several times, you will see that the numbers vary a lot, depending on, even on this machine, which is doing just that in a server, not doing anything else. I run several times, I see that I have perhaps 20% of variation on the performance. So please, that's not a benchmark. That's just a way to have a first touch on the performance. And we see we have something similar, actually, between the two implementations of SYCL there. And so it was taking between 2 and 10 seconds when running sequentially in the CPU. So now, of course, we are going a lot faster. At the moment I made this diagram, I'm not absolutely sure it's the most recent one, and the numbers may be different today. As we see there, I made it 2 years ago. But just to show you what's happening with Insight, we are looking what's happening in the GPU. So that's the end there. The blue is the end of the set of iteration. And when finishing the iteration, we see those red and green blocks, which are the transfers of data, which are done by the buffers accessors. You have seen my solution. I don't say I don't put any copy in it. The runtime is doing it for me, and that's the place where I'm doing some transfer of data. Is there something else to say? So yeah, I noticed there was something strange. It's normally when you have finished iteration, you just want to take back the result. And if you look at Insight, you see that it is sending back things afterwards. I have no idea what, because normally we just need to download the result and let the GPU goes on the next iterations. But as we see with Insight, apparently after the host accessors get the last images, he's sending back things. What things? I don't know. So let's see the step one, the next step, which is to play a little with the list and the selection of device. Because again, we are in the spirit of SYCL there. We are running somewhere. We don't know what are the devices. So let's have a look. Remember the SYCL ls, it's a bonus command of Intel, which lists you the device, but you don't have it with adaptive CPP. It's not in the SYCL specification, but you can write, do your own quite easily. So first steps is move to the device list repository, have a look at the code, play with it. Move to device select, have a look at the code, play with it. We'll do it together also. And the practice is that you try to change your project, your code, the one we used in step 0, so that we can either choose to run on CPU or on GPU with an argument on the command line. So actually make your own selector, looking at argc, argv, and saying, okay, I will run on GPU or I will run on CPU. Let's have a look at those example device list and select. So what do I have in device list? So in device list, I made this this function, which is taking a device as input and displaying many information, which are the platform name, which means more or less what we usually call the backend. Yeah, perhaps it is worth to remind that actually SYCL does not work alone. Generally, there's some kind of backends to address the different kind of device. For example, on CPU, in the implementation of Intel use an OpenCL backend. The one of adaptive CPP use an OpenMP backend. So you will not see the same platform information. All of these depend on the installation, actually. So we have the platform name, the name of the device, the name of the vendor. And just to check, you can look on the device. If you can ask it, are you a CPU? Are you a GPU? Are you an accelerator? In this context, you should understand accelerator as a FPGA, actually. So SYCL was designed with FPGA in mind also. There I'm testing if I'm doing default selector on this device, what is the number which is returned with CPU, GPU, etc. What are doing the selectors? Actually, they are expected to return a number, which is kind of a rank or evaluation of the power of the device. So you can make a selector yourself, which is very simple, just saying 0 or 1 or something like that. But normally, you give a number so that if there is several devices on your machine, SYCL will use the one which returns the bigger number. So we can ask there the CPU, GPU, accelerator numbers. I have this print function, which is just doing the name, printing the name of the device. Try selector is just a templating function to try several kinds of selectors. That would be a way you can use to loop. That's what is done by SYCL LS. And kind of loop, you can loop on all the platform you call SYCL platform, get platform will return you a collection of all the available platforms. For this platform, you can ask, give me the list of all devices. So you can loop on all of them. There I'm just printing what I call the rank, the first one return, the second one, etc., and calling expect to check the information. I remember also that there's no rule about the order of the platforms and the order of the devices. So if on my machine, my GPU is the device of rank 1, on another machine, on yours, it may be different. So in general, you do not use the rank in the list, the rank to select your device. You will rather say CPU selector, GPU, or the one which has NVIDIA in the names, those sort of things. There I'm trying different selectors. I can even try to run it. Let's be to run it on Cassidy. Do I have the network working? Yeah. Okay. Don't worry, those are secret scripts I use to start my Docker. I will use, for example, the Intel one. I will use the image ICPX QDAR. If you're using Docker, don't forget when you start your Docker image, you have some kind of secret commands, -GPU all or those sort of things, or you will not see in Docker container, you will not see your GPU. So if I try, we're doing device list. So my, my script does not guess I'm using ICPX. It should. Okay. I will. Perhaps I'm not up to date there. Let's say. Okay. So there I'm doing. That's the CMake. Then the call to make the build. And then what do we have there as output? So when looping on the platform, then looping on the device, the first one I have is my NVIDIA card. The platform name is NVIDIA CUDA backend. I guess it's the name chosen by CodePlay, which has done the NVIDIA plugin for Intel. The name of the device, vendor. If I ask, are you CPU? Obviously, he say no. GPU, yes. And you see that the default rating, the number returned by the default selector is 500. If I ask him, what is your rating as a CPU, he say -1. That's a way to say for a selector, I'm not a CPU. And as a GPU, his rank is 1000. And then I have my CPU, which is behind an OpenCL backend with different numbers. If there is a check that if I say nothing when doing my queue, I will have the NVIDIA card. If I use the default, I have the same. If I ask for a CPU selector, it is selecting this device, which is the CPU, and with a GPU selector, the NVIDIA card. Okay. That's all consistent. If I look at the device select, I think I have done something which is not that good, but that's just for the demonstration. I've done something based on the rank, I think, yes. There I'm saying on my command line, I want the device rank 0 or 1, and that's my on-the-fly selector. I just capture by a reference this rank, make it greater each time for each new device, and once my current rank is the same asked by the user on the command line, I return equal, so I return 1, and for the other one, I return 0. So that's an easy way to say, I want the device 0, I want the device 1, etc., which we do not do in real life because the rank, they can change from one machine to another. So that's just for the demonstration. So please, on your side, try to do your lambda there in your code, a lambda which will select CPU or GPU depending in the user on the command line has asked for CPU or GPU. Okay. So let's comment on one solution, but there may be many. So actually, I think I reused the existing selectors, tricky writer. So there I'm having a new argument, which which is the first one, which I call device type. I put it in a string. And then when I create the queue, I'm comparing, is this string CPU? If this string is CPU, I'm building, yeah. Actually, let me look. I'm not using a selector in the solution. Because you can first choose your device, then do the queue. Or you can use a selector, as I've shown before. There, I'm doing what? If the device asked is a CPU by the user, then I'm creating a device with the selector, which can also be used actually to create a device, not the queue. I can use the same selector for the device creation. If the argument was GPU, I'm creating a device selected with the GPU selector. And then when I'm creating my queue, I give it device as argument. That's a way, among others. I could use a selector, as I said before, or as I have shown in the slides. You have another way to do it. One thing which is quite easy to do with this kind of mechanisms is that you may want to say, okay, I'm using the default selector, which is selecting the best device on my machine. And after that, I look if is my device a CPU. If it's a CPU, I may start a task which is submitted as a single task, because I know that it will, for my problem, it will be better with a single task on CPU. And if my device is a GPU, I will start the one which is using the parallel for, so that my program, whatever happens, wherever I run it, If there's a GPU, I will do a parallel for. If it's a CPU, I will use a single task. And with SYCL, it's quite easy to do. You can do it without SYCL also, of course, but you have all the material, all the code to do it quite easily there. So back to the practice. So we've seen how to select the GPU. Actually, I think it's better to make the break now. I will break. Can I change the time or not? Yeah? Karim, can I stop now and do the break until 11:15? Was people who want to follow remotely GPU for SYCL, they are already there, so they know about. So it's better to stop there and to do the final things about I/O afterwards. So I suggest now a break until 11:15, if everybody is okay. So go. So half 30 minutes break and back at a quarter to 11.